Welcome all of you. In the last class, we discussed a lot about relaxation phenomenon, concepts, especially varieties of concepts we understood. We started discussing T1 relaxation phenomenon. We knew it is nothing but interaction of the spins with the lattice. We understood that spins gives its energy to the lattice. And the mode of giving energy is stimulated emission. And then the fluctuating field which is responsible for this emission should be at the Larmor frequency. That is what we said. These fluctuating fields are generated because of various tumbling motion of the molecules, especially the chaotic motions. We said especially some motion like diffusion or others can contribute to this. Spontaneous emission is not very less effective, especially in the RF region. So this chaotic motion, when it happens, then spins can give its energy to the lattice. Then this energy is given in the form of a heat. It is very small quantity compared to kinetic energy and dissipates very fast. But why it takes energy sometimes more time? It is because the Larmor frequency which is responsible for local field generated should be in abundance. If it is not there, then spins will not relax very fast. And then what is the mechanism of relaxation? There are several various the same mechanism for creating the local fields. To aid the spins to relax, there are several mechanisms. We understood dipole mechanism, dipole-dipole interaction, where consider two dipoles which are close in space, spatial proximity is a condition, as they are very close in space. The relative orientation or the orientation of them with respect to external magnetic field do not change. As the molecules undergo motion, let us consider one spin, the other spin keep undergoing motion surrounding it, various tumbling motion. Then it keeps on changing, the magnetic field around it keeps changing. The magnetic field at the side of the other nucleus spin keeps changing. That, if it is at the Larmor frequency, can cause relaxation. This is a dominant interaction called dipole-dipole relaxation, which is responsible for relaxation of the spins, especially in the solution state. And I said when the spins are close in space it happens. That is why I said in the case of carbon 13 NMR, if you take proton attached to carbon or some other nuclei which are very close by, their spins relax very fast. Otherwise non-protonated carbons, I told you, like quaternary carbons, you have enormous amount of time to relax. Sometimes when there are enormous time is there to relax, there are external mechanism for which spins can be allowed to relax faster by using external agent. These are called relaxing agents. I gave an example, one such is CRACAC, chromium acetyl acetate. It is happening, and some other things are there. We can utilize that also. So basically we discussed about one of the important dominant relaxation mechanism, that is dipole-dipole interaction. Among several other things, there is of course few other things are very important. One is chemical shift anisotropy. We will today start with chemical shift anisotropy now. We will see how CSA is going to aid in relaxation. The CSA, of course, you know why it comes. It is because of asymmetrical, unsymmetrical or asymmetrical distribution of charges surrounding the chemical bond. So if there is a charge density which is not symmetrical, if there is asymmetric charge distribution of electrons, because then chemical shift anisotropy arises a large number. Chemical shift anisotropy depends upon charge distribution at the site of the nucleus. In the case of CSA, again in the case of solution, CSA is average out due to rapid tumbling motion of the molecules. Molecules undergo rapid tumbling motion. As a consequence, the CSA is averaged out. Remember I told you in the very first class, among the internal interactions, CSA, dipole interactions, they all get averaged out in solution. It is not possible to measure it in solution state. But their mechanism aids relaxation. You may not measure CSA in solution state, but their motion, the CSA which is present, which creates the local field, will aid in relaxation. So CSA is another thing which comes because of rapid, which gets averaged out in solution because of rapid tumbling motion, can also stimulate relaxation. And if the CSA is a large value, it can stimulate relaxation, and if it is when it is sufficiently strong, especially fluorine 19, carbon, phosphorus 31, etc., they have large CSA. especially in also metals, many metals, they exhibit such relaxation phenomena because of CSA. Okay. So, CSA is the dominant phenomenon of relaxation in some nuclei like this. This is one another source of relaxation, but no source of relaxation is unique. Everything could be present simultaneously, various phenomenon is present. Okay. For example, if I take the CSA, important point you should know is relaxation due to CSA is field dependent, because CSA is field dependent. So, contribution to relaxation, you know, chemical shift anisotropy is field dependent, chemical shift is field dependent, I told you, it varies linearly with the magnetic field, external magnetic field. Hence, its contribution to relaxation is higher at higher field. Higher the magnetic field, higher the chemical shift anisotropy, larger the value. So, it relaxes faster. So, the relaxation you because of CSA is field dependent. Take for example a molecule like this. It is a simple molecule called selone. Proton selenium NOE was done this like this. No, NOE experiment. I will tell you what is NOE, do not worry. To irradiate one of the protons to see the effect of change in the intensity, that can help you to find out about spatial proximity. In NOE, in the next class we will discuss all those things. And NOE from proton selenium 77, when they tried to do the NOE, it was not possible to detect NOE. NOE is very weak, they could not detect at all. So, the dominant relaxation phenomena in this case was CSA, because NOE comes because of dipole-dipole mechanism. I will come to that later. NOE, main source of NOE is dipole-dipole interaction. Since they could not see NOE, it could not be seen experimentally between selenium and proton. It is assumed or it is confirmed that the dominant relaxation mechanism in this case is CSA, and because this is ineffective. So, in this molecule, see, look at this one, selenium 77 T1 relaxation rate when measured. How we measure we will see later. It was linearly dependent, because CSA is linearly dependent. See, as a function of magnetic field, CSA, you can see the T1 was here at some magnetic field, and for this magnetic field it is here, and here at 50, this is. So, that shows when there is a relaxation is T1 dependent like this, it is understood the significant relaxation phenomena or mechanism is CSA in this molecule. And also confirmation is NOE phenomena could not be seen between selenium and proton, which comes because of dominant dipole-dipole mechanism. So, CSA is another dominant mechanism and seen largely larger line width at higher magnetic field if there is large CSA. This is the understandable phenomena, because if CSA is field dependent, as go to higher and higher magnetic field, the CSA becomes larger and larger, and then it gives rise to larger line width, especially in the solution state. You do not measure CSA, but it causes relaxation phenomena. Like I told you, we can see that if there is unpaired electron relaxes faster, I told you. As a consequence, the signals are going to be broad. Similarly, CSA, as you go to higher and higher magnetic field, has larger anisotropy, means line width becomes larger. This is why one of the reason some metals and nuclei which have unpaired electrons, which has fast relaxation or CSA is larger, is studied only at lower magnetic field, not at higher magnetic field. At higher magnetic field it is very difficult. As a consequence of one such study of such nuclei, generally it is preferred to study at low magnetic field. See, for example, in this molecule, the CSA relaxation is dominant, especially in this molecule. It was looking for the platinum complex. There are platinum acetylates in this molecule. Okay. This is at 80 megahertz and at 400 megahertz. Two spectrometers, spectrum was obtained. Okay. So, now this is the 1s spectrum of complex. This is 1s spectrum. Now, there is a platinum coupling with this. Platinum can couple to this proton, 2-bond coupling is there. But this platinum also has little abundance. So, intensity pattern is quite reasonable here. If it is very, very small intensity, they are called acetylates. I think we discussed this in previous course. This course I did not talk about it, but those who are interested can see. But maybe when I discuss as HSQC and others, I will tell you something about little bit about what is satellite and everything. The satellite intensity you see is quite sharp, and intense at 80 megahertz. The same sample, same spectrum, proton spectrum, and recorded at 800 400 megahertz, you see the satellites become broad. And if you go to even 800 megahertz data set, what will happen? This will completely disappear. See, this satellite is coming because of coupling of proton with platinum with proton. That is why they are satellites. And these satellites become broad, means the relaxation time is of this CSA is quite large. Okay, as go to higher and higher magnetic field, it is broadening the signal. And if you go to very high magnetic field, you may not be able to see the satellite at all. It will become completely broad. So this is why CSA is one of the important dominant relaxation phenomena. That is what we discussed. Now we will understand something called spin rotation relaxation. This is another interesting phenomenon. Various phenomenon is there for understanding. Now let us say in your molecule you have a rapidly rotating group. What is that? Take for example CH3 group or CF3 group, or the molecule itself for a particular ring undergoing fast rotation. Some rotation is there. Rapidly rotating group CH3. I have a C3 here, 3 protons along the CC bond. This may be undergoing very fast rotation. Then what will happen? The magnetic moment generated by this rotating group, because of that, electronic and nuclear charges will be present. Okay, and this one that produces the field because of the fluctuating charges. This field fluctuates and aids in relaxation. It is one of the mechanism of relaxation. Please understand, the field produced because of the fluctuation of the rotating electronic and nuclear charges, you have a dominant relaxation mechanism, not dominant relaxation mechanism. And this is very effective, especially for small molecules, symmetrical molecules, or freely rotating methyl group, CH3 group, CF3 group, etc. If they are present, they will be undergoing fast rotation, and as the tumbling frequency of the methyl groups rotates faster and faster, then the relaxation increases, relaxation efficiency increases. So this is the important thing. The spin rotation relaxation is arrived, you can see basically you can see in small molecules, symmetrical molecule containing fast rotating groups like methyl group and CF3 groups. Now we will talk about quadrupolar relaxation. Remember I told you when we were discussing about internal interactions, I said for the nuclei greater than spin half, there is one type of interaction which is called quadrupolar interaction. It is because of it is an electrical interaction. I told you, interaction of the electric magnetic moment with the electric field gradient, that can give rise to some sort of a interaction, quadrupolar coupling. But in the solution, the quadrupole coupling is not seen, it is averaged out. Okay, but though it averages out, but it aids in relaxation. That is called quadrupolar relaxation. Quadrupolar nuclei possess electric quadrupole moment in addition to magnetic dipole moment. And this is because we have electric field gradient at the site of the nucleus. As a consequence, it creates quadrupole moment. And then electric field gradient that is modulated as a molecule tumbles in solution. There is electric field gradient which is produced at the site of the nucleus because of the electric quadrupole moment and the interaction of the electrical quadrupole moment with electric field gradient. So EFG that is generated at the site of the nucleus is varying. It keeps fluctuating as the molecule fluctuates. So EFG gets modulated when the molecule is undergoing tumbling motion. So this can create relaxation. For all these things, when the molecule undergoes rotation, whether it is a spin rotation, whether it is a dipole-dipole interaction, or whether it is a CSC or it is quadrupolar relaxation, finally what happens? The magnetic field at this tumbling, because of molecular tumbling, the magnetic field, local field generated at the site of other nuclei is changing. So as a consequence, there is a relaxation, it aids relaxation, there is a phenomenon for relaxation, and this is what happens, it stimulates relaxation now. Okay, this quadrupolar relaxation. Sometimes quadrupolar relaxation is so large, I do not want to go into the details of that. Remember, some nuclei like exotic nuclei have a very large quadrupole moment of the order of several megahertz, 5 mega, 10 mega, 20 megahertz. Remember, it is a huge number. What are the interaction strength? Interaction strength, Zeeman interaction strength is larger among all the external interactions. Then we have, if you look at the internal interactions, dipole is larger, dipole-dipole interaction. Then comes CSA, then comes spin rotation, then comes J coupling, like that. Chemical shift interaction is second after dipole coupling, then J coupling, like that it goes. Whereas for the spin greater than half nuclei, quadrupole interaction becomes dominant. It is really dominant. This sparks quadrupole coupling. The quadrupole interaction, when it becomes dominant, generally, then what happens? You will not see the coupling of this quadrupole nuclei with any other nuclei. For example, you take CHCl3. If you take CHCl3, look for the proton NMR, you will see coupling to carbon 13, as I said, appear as satellites. See C13 NMR, you will see coupling with proton and you get a doublet. But what about chlorines? Chlorine 35 and chlorine 37, they have spins. They are quadrupolar nuclei. But they will not contribute to coupling because the relaxation is so far. The quadrupole coupling is so large, it will not participate in this and relaxes faster, and you will not see the coupling. Especially the quadrupole coupling is very, very large. You will not see the coupling with the other nuclei, especially when the quadrupolar nuclei are close by, are coupled, are interacting. For example, you take CDCl3. If you take the CDCl3 molecule, I look for the carbon 13 NMR, and very interestingly, what I am going to see is a triplet like this. Not triplet, 3-line pattern. This is a 3-line pattern of equal intensity. And this separation gives you CD coupling, coupling between carbon and deuterium. So this is an interesting thing we can measure here. And this is very large. It is coupled to a quadrupolar spin, spin 1. Deuterium is a quadrupolar nucleus, spin 1. But still, in reality, if the quadrupolar coupling is very, very large, you will not see the 3-line pattern at all. In fact, it will smudge and give rise to a broad hump generally in some other nuclei like chlorine 35 and chlorine 37 in CSCl3. That is what I said. But in this case, you are going to see it. That is because this deuterium has a very small quadrupole moment. As a consequence, the coupling of carbon to deuterium is clearly seen in some cases. For example, chlorine 35 and chlorine 37, which has spin 3/2. We will not see that because this is what is called quenching. We call it quenching by the rapid relaxation. This is called relaxation enabled decoupling. This is called relaxation decoupling. You will not see the coupling of chlorine with carbon because of rapid relaxation. This is called quenching. Okay. So take for example nitrogen 14, proton NMR spectrum of nitrogen 14 H4. It is an ion, NH4 ion if you take. I take 1H spectrum. It is 1:1:1 triplet, not triplet, you should not in principle called. In the NMR jargon, triplet is 1:1 intensity, commonly used. But we say 3 lines of equal intensity. Okay, loosely you call it triplet, doesn't matter. But it should be called 1:1:1 3-line pattern. The NH4, if you take the 1H NMR spectrum, it is going to be 3-line pattern of equal intensity. Why it is coming? Because N14 has spin 1, like deuterium. We saw in CDCl3, with deuterium coupling. Here also you are seeing the coupling. Okay, this is without coupling. And there is something which was done for this molecule, acidification, before acidification, and there was no coupling seen, but here you are seeing the coupling after acidification, because the symmetry induced reduces the quadrupole coupling after some chemical modification. The quadrupole relaxation becomes very, very fast. Quadrupole relaxation rate is it reduces, quadrupole relaxation rate reduces. Then coupling between N14 and proton of the order of 51 Hertz is very clearly visible. And before acidification, you see, you don't see anything, no coupling seen at all. Whereas after doing some chemistry, you see that proton is coupled to N14, giving rise to 3 lines of equal intensity with a measurable coupling of 51 Hertz. Lines are quite sharp. Okay. Look at this one. This is another very interesting molecule. It is BF4 ion. Bromine has 2 isotopes we discussed in one of the molecule analysis of the heteronuclear spectra. Bromine 10 and bromine 11. Bromine 11 has spin 3/2. Bromine 10 has spin 3. And this has 20% abundance. This has 80% abundance. So now we look for the fluorine NMR. when fluorine is coupled to bromine, how many peaks we expect? Remember 2 Na plus 1 I apply. This also we discussed in one earlier case. In the case of bromine, I is equal to 3 by 2, 2 into N is equal to, there are only one bromine, into 3 by 2 plus 1. So what will happen? 3 plus 1, you will get 4 lines. So for the boron 11, you are going to get 4 lines of equal intensity. And this separation gives you boron 11 and fluorine coupling. It is seen. 1.4 Hertz J coupling you could see. Such sharp lines you could see in spite of the coupling of proton with the quadrupolar spin. Look at boron 10, I is equal to 3. Put I is equal to 3 in the same equation. 2 into 3 plus 1, it will be 7 lines. You see 7 lines of equal intensity. With a coupling of 0.5 Hertz you could see. In both the case spin 3 and 3 by 2, its coupling with fluorine nucleus is seen. Normally when you do not see that thing, especially in some cases where there is a symmetrical charge distribution more or less at the site, somehow the quadrupole coupling or quadrupole moment reduced significantly, we are going to see this type of coupling. And why it is small intensity compared to that? Because the abundance is only 20%, this is 80%. So it should be 4 times larger intensity. And this is very small, 7 line pattern is of equal intensity. So these are the thing. So there are various other mechanisms of relaxation like J anisotropy, various. I did not discuss all those things. These are all some important parameters for relaxation which I discussed. Now you may tell me, fine, we are discussing about the T1 mechanism, T1, what is T1, what is the concept of T1, everything. But what is the value of T1? How much time it takes to relax? I said it takes some time for the spins to relax to thermal equilibrium along that axis. Clear, understandable. But what is the value of T1 if you ask? I have to find out. Is it in milliseconds, seconds or hours, days, minutes? I must know that. So approximate values of the T1 just to tell you. But it is not a rule as such. It can be large, it can significantly deviate from what I am telling here. I said proton T1s are in the range of 0.5 to 5 seconds. It is not a dogma, it should be like that. It is an average, it can be of that order. Generally proton T1s in solution state, I am talking in solution state is of this order. It can sometimes be hours, days and minutes also. It can go to several hours, it can go to minutes or it can go sometimes to days depending upon the fluctuating field available at the site of the nucleus for the spins to undergo relaxation. Otherwise it can be fast like this. And whereas carbon 13, if you look at T1s, there we can vary from a few seconds to a few tenths of seconds. That is also quite large. Okay. Especially in rigid or less mobile molecules, T1 can be minutes, hours and sometimes days. Simple example, you take solids. It is not mobile, rigid solid you take it in the powder form or a crystalline form. There is no mobility for the molecule. Internally molecule may be undergoing rotational motion may be there. But there is no translational motion. Molecules are fixed in space in crystal or in a solid, unlike in solution state. So less mobility. T1s can be large, it can be minutes, it can be hours and days. So T1 depends upon the mobility, and especially that is the reason why T1 in the case of solids are very, very long. It can go to several hours also. So now we can ask the question, how does T1 affect it? So I know the value of T1. I know what is the range, approximately range of T1 values in different situations. But how does T1 affect me? Why should I worry about it when I want to do the experiment? Of course, the T1 information gives you more information, more about the dynamics of the molecule. I told you long back when we started this relaxation phenomenon. It gives you information. If you want to derive information about the dynamics of the molecule, this T1 and T2 phenomena is very useful. Fine. But why should I know the value of this? Is it important for me to do the NMR experiment? Of course yes. The reason is this is the expression we derived for the magnetization for the spins to attain thermal equilibrium after it is disturbed. This is MZ, Z magnetization to attain M0. When it comes to the original magnetization, this follows exponential law. There is an exponential growth. Now what I will do is, this is exponential 1 minus e to the power of t by t1. What I am going to do is, we will substitute for t by t1 different values. What we will do is, once we will say, let us say I am going to put t is equal to t1. T is equal to t1. What will happen? a to the power of minus 1. It is 1 over E. 1 over E is a 2.6752, you know that number. You calculate that 1 over E, what is that? Then it turns out to be 1 minus that E, it is 63. Okay. So now put T is equal to T1 is equal to 2 times T1, it is 86. Put it is equal to 3 times T1, it is 95%, or 5 times T1, it is almost 99%. So if you want the spins to come back to thermal equilibrium, maximum magnetization, if it has to grow along z axis, you have to wait 5 times the log T1, and T1 for different spins in the in the molecule will be different. In the same given molecule, different functional groups, different nuclear spins can have a different T1. So if you have to do the experiment, you should know what is the longest T1 of any spin in your molecule. 5 times that T1 value you have to give the delay between the pulse, successive data accumulation of signal. Successive data accumulation should be of the order of 5 times T1. Only then you can get maximum signal, because by the time if you wait for 5 times T1, 99.33% magnetization would have come back to z axis. So you apply another radio frequency pulse to collect signal, you get 99% signal. So that is important. So you should know the T1 to get the then you can set up your experiment to get the signal. For example, your T1 is of the order of, let us say, several minutes, some 50 minutes, 30 or 40 minutes, and you do not know the T1 value. Start acquiring the signal, send first RF pulse and start collecting the signal. Then second time immediately after collecting signal, wait for 1 or 2 seconds and send another pulse. You will not see the signal at all, you will acquire only noise. The reason is spins have not relaxed back to thermal equilibrium, it has not come back to z axis. So as a consequence, the T1 value is very important to know, so that you can set your experiment accordingly. The T1 affects the routine NMR experiment in this way. If you want to repeat the experiment for signal averaging, if you want to after acquiring the data, if you want to send another pulse to collect signal, you must wait at least 5 times the longest T1 available in your sample, in your molecule. Okay. So with this, longer T1 is the time which is required for signal averaging. For maximum recovery of magnetization, we need to wait for 5 T1 before applying another pulse for signal averaging. So with this T1 we have understood a lot. We will talk something more about T2 relaxation now. T2 is also very important relaxation phenomena. So far we discussed about, but we have not even still discussed about how do we measure T1. We will come to that after giving the conceptual ideas of T2 relaxation also. Then we will go to the experimental aspect to measure T1 and T2. That is simple. So what is the T2 relaxation? There are two important relaxation phenomenon, spin lattice and spin spin. This is called spin-spin relaxation. T2 relaxation is the process by which the transverse component of the magnetization decay in phase or decay or D phase. That means if I apply the radio frequency pulse to the magnetization which is along z axis, bring it to xy plane, I told you it will go back to z axis with time, that is T1, but before that it will start dephasing in the xy plane. Instantaneously, as soon as you bring the magnetization to x axis, there is a statistical phase coherence. All the spins will be aligned along this axis, all spin vectors, maximum signal you get. With time, again, because of the local fluctuating magnetic fields at the site of different nucleus, the spins vectors start defacing, they start moving in the xy plane. Then the total vector addition of all the things if you take and look at the signal intensity will come down. And if you wait for a sufficiently long time, it so happens all the spin vectors here get completely decay or dephase in the xy plane. This is called decay of magnetization in the transverse plane. This is another type of relaxation called spin-spin relaxation, or also called transverse relaxation. Remember two relaxation mechanism? Lattice relaxation is the growth along z axis. Spin-spin relaxation is the decay in the xy plane. This is the transverse. This is called a transverse plane. Decay of magnetization in the xy plane. Xy plane is called a transverse plane. It is called transverse relaxation is T2. Decay along z axis, it is also called longitudinal axis, is called T1, also called spin lattice relaxation. And now T2 relaxation, how it happens? First, initially there is a Boltzmann distribution along z axis that has to be preserved. Initial value of m in the z axis is mz. Immediately after RF pulse is applied, net magnetization comes to mxy. I told you statistically there is a temporary phase coherence. All nuclear magnetic moments will be aligned in a particular axis, and net magnetization is the sum of all magnetic vector in the xy plane or in particular axis. The maximum signal will be there. Mxy will be maximum immediately after bringing the magnetization to the x transverse plane. So, this is what happens, bring the magnetization to xy plane by applying the pulse. Now, in homogeneity of the magnetic field and small differences in the local fluctuating fields experienced by these nuclear spins causes the spins to lose phase coherence. All the nuclear spins vectors will be aligned along this axis. There is a phase coherence, but this phase coherence will be lost. That is because there is a local magnetic field experienced by the spins are different. They keep changing, they keep fluctuating. Different nuclear spins experience a different magnetic fields. So, as a consequence, there is no phase coherence. So, when there is no phase coherence, individual magnetic moments start fanning out. They will start going out from the particular x axis, start moving all across the xy plane. And then vector addition you do. When you do the vector addition in the xy plane, some vector in this direction, some in the opposite direction, they get nullified. Similarly, when all nuclear magnetic moments completely get dephased in the xy plane, if you take the vector addition of all of them, there is no signal at all. It is totally 0. Magnetic moment will not be there. In the total magnetization will not magnetic moment, the total magnetization, some addition of all the individual magnetic moments if you take in the x transverse plane is not there, because they are completely dephased. So, vector addition is 0. Okay. This is what you understand. Remember, I said this in the T1 case. T1 was growth along this axis, the same thing what I showed. It immediately you bring it to xy plane, there is a phase coherence. Now, all nuclear spin vectors are in this axis, x axis. Now, some will start going like this, some will start going like this. Those which goes along this axis, remember when we discussed about the evolution of magnetization, we discussed these are all called fast moving components and slow moving components. Some moves faster like this, some moves like this. As you keep on waiting for some time, slowly the fluctuating magnetic field makes the spins lose phase coherence, they start dephasing like this. And after some time there is a complete decoherence. Now, take the average of this, take the vector addition of all the magnetic moment vectors, it is 0, because at any instant of time if there is one vector like this, you can find another vector in the opposite direction. So, vector addition of all these things becomes 0. So, this is a total dephasing time. Now, the time which is required for the magnetization which is in the transverse plane, if you immediately bring after a 90 degree pulse, with the instantaneous phase coherence, the time it requires for the spins magnetic moment vectors to lose complete phase coherence is called T2. It is called spin relaxation mechanism. This is called a T2 relaxation, also called spin relaxation, where the transverse components will completely dephase. So, the magnitude of the xy component of this, if you take the vector addition, will 0, and this is again is an exponentially decaying function. Like exponential growth of T1 along z axis, this is an exponentially decaying function along in the transverse plane, both the x axis and y axis. So, that is why mx component of the magnetization is 0, my component is 0. That is why you have a receiver here, you get no signal, you have a receiver here, you get no signal. Both are 0 after spins completely undergo dephasing. And for most spin off nuclei in small rapidly tumbling molecules in low viscous solution, it is the field inhomogeneity that provides the dominant contribution to observed line width. It is rarely possible to obtain G2. Only for small molecules T1 is approximately equal to T2, not exactly, that is the wrong statement, it should be approximately. For large molecule T2 is much shorter than T1. Okay. So, now more about T2 and other things we will discuss next class, and then we will understand something more. So, since time is up, I am stopping here. Now in this class we understood all about T1 mechanism and everything, and also I introduced what is a spin relaxation. In the spin lattice relaxation we discuss a lot about phenomenon of relaxation like dipole-dipole interaction, chemical shift anisotropy, quadrupole coupling, all those things, how they contribute to the and generate local fluctuating fields at the site of the nucleus to ensure that they are at the larval frequency, some of them are at larval frequency, and they will ensure that spins gives energy to the system lattice and then go back, relax and go back to thermal, attain thermal equilibrium, go back to Z axis. Various things we discussed. Then we also understood what is a spin relaxation. It is nothing but the dephasing of the magnetization in the XY plane. We discussed that. You understood what is this thing, and it again requires fluctuating fields also. Okay, and then this happens simultaneously along with T1. We will discuss that later, and especially in small molecules, T1 is approximately equal to T2, and for large molecule T2 is much shorter than T1. We discuss more about these things in the next class. I will stop here. Thank you very much.